So we spent quite a bit of time talking about Ka and Kb. So now let's go ahead and spend some time talking about the relationship between Ka and Kb. So first off, what I want to do is I want to look at Ka for this particular reaction where we have our acid ammonium. It goes on to form its conjugate base ammonia and then the hydronium ion. So Ka, the expression for this first reaction would be NH3 times hydronium all out over ammonium. If we were to look at the opposite reaction, where we're looking at ammonia as being the base and forming its conjugate acid ammonium, what we would find is Kb for this particular reaction is concentration of OH minus times the concentration of ammonium all over the concentration of ammonia. Well, what's the net reaction whenever we combine these? So whenever we start to combine these two reactions, we would see that the ammoniums would cancel out, the ammonias would cancel out, and we would be left with something that looks like this. 2H2O yields hydronium plus hydroxide. So we've actually seen this before. This looks a lot like Kw. In fact, this is Kw. So remember that Kw is equal to the concentration of hydronium times the concentration of hydroxide. And at 298 Kelvin, Kw is 1.0 times 10 to the negative 14th. So how does Kw relate to Ka and Kb? So previously, whenever we first started looking at equilibrium constants, we looked at combining reactions and then trying to calculate a new equilibrium constant. So we know that if we're just combining reactions in an additive manner, we will actually multiply the equilibrium constants together. So what we'll end up seeing here is Kw is going to be equal to Ka times Kb. So this is a really useful relationship if you're going to be dealing with equilibrium constants. But we can actually perform another operation to get another expression that will seem quite familiar at first. So recall that whenever we were looking for the pH, we took the negative log of hydronium. Whenever we were looking for the pOH, took the negative log of hydroxide. And then we wrote an expression that we said, well, 14 is equal to pH plus pOH. Whenever we took the negative log of this whole expression. So what we can do is we can actually do a similar process for here. We can take negative log. So we know that Kw at 298 is 1 times 10 to the negative 14th. So the negative log of that is 14. And then just how we had pH was the negative log of H3O plus, if you take the negative log of Ka, you'll get something known as the pKa plus negative log of Kb would be equal to pKb. So pKa plus pKb is equal to 14. And this is another really useful expression that we will use as we go on. So let's go ahead and look at a few examples where we look at finding Ka or Kb, and then also looking at pKa and pKb. So in this first example, you are given Kb for trimethylamine, and we are asked to calculate Ka for the trimethylammonium ion. So what we'll have to do in this case is we'll have to write out our expression. So Kw is equal to Ka times Kb. Well, if we're trying to calculate Ka, Ka will equal Kw over Kb. So now all we have to do is plug in our values. So Kw is 1.0 times 10 to the negative 14th divided by Kb, which is 6.5 times 10 to the negative 5th. When we plug this in, making sure we follow our order of operations, we'll end up with Ka is 1.5 times 10 to the negative 10th. So you can find Ka if you're given Kb. You can also find Kb if you're given Ka. So in this case, what we are given is Ka for HCN, and we're asked to find Kb. So again, we know that Kw is equal to Ka times Kb. So Kb would be equal to Kw over Ka. We can substitute in Kw, 1.0 times 10 to the negative 14th, all over Ka, which is 4.9 times 10 to the negative 10th. And that will equal 2.0 times 10 to the negative 5th. Sometimes you may be given pKa's or pKb's and then be asked to find Ka's or Kb's. You just need to keep all of these relationships in mind as we're moving forward. So on this last example, what we want to do is we want to look at pyridine, and then pKb is given to you. It's 8.74. And then it asks, what is the value of pKa for the pyridinium ion? So in this case, we know that pKa plus pKb is equal to 14. So that means if we're looking for the value of pKa, pKa is equal to 14 minus pKb. So then, whenever we plug in, we'll end up seeing that pKa is equal to 5.26. And in one of our following units, whenever we start to look at titrations, we will see the importance of pKa and how we can use pKa to determine strength of an acid or pKb to determine the strength of a base. So that concludes this brief lecture on Ka's and Kb's, their relationship, and then also pKa's and pKb's. Remember, smash that like button.